morning, children. In today's class, we are going to learn about continuity. Continuity, a most frequent word that we use. A series that continues. A serial that continues. Yesterday's talk continues today. So what does this word continuity mean? Continuity tells us without break. Suppose I draw a curve like this. Does it go continuously? Yes, because there is no break at all. Suppose I have another curve like this. There is a break here. So the curve after this point, see here and here, there is a break. Before it goes in some way, after this point it goes in some other way. So I say this point is a discontinuous point. The curve is discontinuous at x is equal to x naught. Just by looking at the curve in a particular interval. See, for example, the same curve. When I take this as x-axis, y-axis and origin. If suppose I want between this A and B. In between A and B, look an interval A comma B. So I call an interval. In this interval, the curve is continuous. Okay, so I can call even in the closed interval AB. What do I mean by closed interval? A and B are inclusive. So in a closed interval AB, that is from A to B, there is no break I can see in the curve. Suppose I extend the limit like this way. Say this is x-axis and in this interval AC. Now the interval is in I1, the interval AB. It is continuous, but in I2, the interval AC, there is a point where it is breaking. So, the continuity depends on the interval. I should say where it starts and where it ends. From the starting point to the ending point, if there is no break at all, I can say the curve is continuous. But from the starting point to the ending point, if there is a break, I should tell f of x, the curve f of x is having a point of discontinuity here inside the interval. How are we to define it mathematically? Now I should say at a particular point, if I want to find out, check whether left limit exists, check whether right limit exists, and the limit value should be equal. This is the idea for existence of limit, which we had learnt in the previous exercise. Once I know limit exists, find out the function value at that particular point. Find the limit value, find the function value. Both should exist. And if limit value and function value are equal, I can declare the function is continuous. So how do I define? I should say limit x tends to A, or I can say some x naught. Limit x tends to x naught, f of x is some L, let me say. Function value also should be L only. So I should say limit should exist, function value should exist, and they must be equal. So whenever I say limit x tends to x naught, f of x equals to f of x naught, I can declare f is continuous. Continuous where? At the particular point x naught. If suppose the function is continuous at every point in the interval, I can declare f of x is continuous in the interval a, b. Or I can say f of x is continuous in the interval a, c. Suppose there is one point in the interval where it is not continuous, I should say the function is not continuous in that particular interval. If f and g two functions continuous at a point x0, then we can declare f plus g, sum of the functions, f minus g, the difference of the functions, f into g, the product of the functions, are also continuous at x is equal to x0. When I say the quotient f by g, I need to say it is continuous at x is equal to x0 provided g of x, the denominator, is not equal to 0. And when it is a case of composition of functions, f composition g, we can still say it is continuous at x is equal to x0 if f is continuous at g of x0 and g is continuous at x0. So here alone we have a special case where we say f is continuous at g of x0 and g is continuous at x0. What do we mean by f composition g of x? F of g of x. So g for x. So I must say g is continuous at x0. Where f, I need g of x. So f is continuous at g of x0 and hence we define f composition g is continuous at x is equal to x0 if f is continuous at g of x0 and g is continuous at x0. Let us see some examples for continuous functions. Constant function, say f of x equals 7, f of x equals 2. These are continuous. In general, I can say f of x equal to k is continuous. F of x equal to x power n, where n should be a positive integer. So these power functions are continuous. When it is the case of a polynomial of degree n, this is again a continuous function. So in all these cases, we never see any denominator. Rational functions, when we consider it is p of x by q of x. These are again continuous provided q of x is not equal to 0. Circular functions, sin x, cos x, these functions are continuous everywhere in the number line. So, sin x, cos x, rational, polynomial, power function, constant functions, all these functions are continuous in R, that is from minus infinity to plus infinity. Provided if denominator exists, it mustn't be equal to 0. But when I say tan, cot, secant, cosecant, we have them as tan x is sin by cos. So I have denominator. Cot is cos by sin. Still I have denominator. Secant is 1 by cos and cosecant is 1 by sin. So according to the denominator not equal to 0 terms, we are redefining the domain for everything. So we will say these functions are also continuous in their respective domains. Modulus function is continuous throughout. So this is continuous in the entire real line. Exponential function e power x is continuous in R. Whenever I say R, we mean from minus infinity to plus infinity. Log x, when we see, it is defined only when x is greater than 0. Logarithm of negative values are not defined. So logarithmic function is continuous in 0 infinity. Now there is a question, how to check whether a function is discontinuous. To find points of discontinuity, put the denominator 0. If possible, eliminate where and all the denominator becomes 0 from the real number line so that I can make it to be continuous. Here is a question, greatest integer function which we had learnt in the earlier chapters. This is discontinuous at x is equal to 0. Now, there are some special words for discontinuity. Jump discontinuity and removable discontinuity. The word jump discontinuity. When do I say? When left and right limit exist, but they are not equal. So, left limit will be here, right limit may be from here. So, there is a jump. So, such problems, we say it is a jump discontinuity. Now, removable discontinuity. Here, left limit will exist, right limit will exist, and they are equal also. At a particular point, say x is equal to x naught. But the function is not defined at that point. So, we can remove this discontinuity by redefining the function to have the limit value at the point of discontinuity. So, as we see the exercise problems, we will understand these concepts still more. So, let us see exercise problems in detail. Exercise 9.5, question number 1, prove that f of x equals 2x square plus 3x minus 5 is continuous at all points in R. It is a polynomial function. So once I identify it as a polynomial function, I can immediately conclude it is continuous at all points in R. Question number 2, examine the continuity. Given x plus sin x. X is continuous, sin x is continuous. So I can say the sum x plus sin x is also continuous at all points x belonging to R. X square cos x. X square is continuous. Cos x is also continuous. So x square into cos x, the product is again continuous at all points x belonging to R. Third subdivision, f of x is e power x tan x. Again, it's a product. E power x is continuous for all x belonging to R. Tan x is also continuous for all x except odd multiple of pi by 2. So, we will remove where it is not continuous alone. So, the domain of tan x is R minus odd multiple of pi by 2. So, whenever I say odd multiple, we write 2n plus 1 into pi by 2 where n is an integer. So, e power x into tan x, the product is continuous only in all x belonging to R minus 2n plus 1 pi by 2 where n is an integer. Fourth subdivision, f of x is e power 2x plus x squared. E power 2x, exponential function continuous for all x. X square is again continuous for all x belonging to R. Therefore, the sum e power 2x plus x square is also continuous for all x belonging to R. Fifth subdivision, f of x is x into natural logarithm ln symbol ln of x. So, logarithmic function is continuous in the interval 0 infinity. Remember, it is open interval 0 infinity. And x is continuous all over. But when I multiply, I will restrict the interval as this. So, x into logarithm of x is continuous for all x in the open interval 0 infinity. Sixth subdivision, f of x equals sin x by x square. So, here we have a rational function. The numerator sin x is continuous for all x and the denominator x square is also continuous for all x belonging to R. But whenever we have rational function, ensure that the denominator is not 0. So, x square is 0 when x is equal to 0. Eliminate 0 alone from the real number set so that the given function is continuous for all x belonging to R minus 0. Seventh subdivision, f of x equals x square minus 16 by x plus 4. The same idea as the previous section. We have a rational function where the numerator is continuous and the denominator is also continuous. But the denominator becomes 0 when x is equal to minus 4. So eliminate minus 4 alone from the set of reals, so that the given function f of x is continuous for all x belonging to R minus 4. Eighth subdivision, we have the modulus function and we learnt modulus function is continuous for all x belonging to R. So mod x plus 2 is continuous, mod x minus 1 is also continuous, and so the sum of it is definitely continuous for all x belonging to R. Ninth subdivision, we have mod x minus 2 by mod x plus 1. The numerator and denominators are continuous for all x being modulus function, but the denominator becomes 0 when x is equal to minus 1. So we say f of x is continuous for all x belonging to R except minus 1. 10th subdivision, f of x equals cot x plus tan x. Cot x is cos x by sin x and tan x is sin x by cos x. The denominator sin x is 0 when x is any pi, or I can say even multiple of pi by 2. Tan x can be written as sin x by cos x. The denominator cos x is 0 when x is odd pi by 2. Now we are adding both. So combine both and eliminate from the reals. Here I get any pi, or in other words even multiple of pi by 2. Whereas in the second case I get odd multiple of pi by 2. Combining which we simply get a multiple of pi by 2. So the given function is continuous for all x belonging to R other than a multiple of pi by 2. So R minus n pi by 2, where n is an integer. Question number 3. Find the points of discontinuity of the function f where f of x is 4x plus 5 if x is less than or equal to 3, 4x minus 5 if x is greater than 3. When you are given a problem like this, we need to find this number. Below 3 it is defined in one way, above 3 it is defined in some other way. So the maximum cases at 3 we need to check for discontinuity. What is f of 3? 3 is inclusive here. So when I want function value, put x is equal to 3. 4 into 3 plus 5. And my answer is 12 plus 5, that is 17. To find left limit. Left limit claims us x is below 3, a little below 3. So below 3 I am here. So I should substitute wherever x comes 3 minus h because it is left limit and limit h tends to 0. As I substitute here, wherever x comes, I am putting 3 minus h plus 5. As I put h 0, we get 4 3s are 12 plus 5 and my answer is 17. Right limit. Wherever x is coming, we have to put 3 plus h. Take limit h tending to 0. 3 plus h comes here. So I have to substitute here. 4 into 3 plus h minus 5. As I put h tending to 0, I get 12 minus 5, that is 7. Left limit I arrive at 17. Right limit I arrive at 7. The left and right limits are not equal. So we say f of x is discontinuous at x is equal to 3. Because left and right limits are not equal, I can declare this as jump discontinuity. Remember, whenever the left and right limits are not equal, we can call it as jump discontinuity at the point x is equal to 3. Subdivision 2, f of x equals x plus 2 when x is more than 2, x square when x is less than 2. So the problematic number is 2. It will be continuous in all other points. Let us check discontinuity at the point 2. What is the function value? When x is equal to 2, equality comes here. Let us substitute here. I get 2 plus 2. My answer is 4. So this I will call function value. So what is the function value? I just substitute x is equal to 2 in the function. In this interval, because 2 is inclusive here. Now we need to find the left limit at 2. So put x is equal to 2 minus h and take limit h tending to 0. 2 minus h means I am below 2. That is, I am here. So what is my answer? X square. In the place of x, put 2 minus h. It is 2 minus h the whole square. As I put h 0, I just get 2 square, which is 4. To get right limit, put x is equal to 2 plus h and take limit h tending to 0. 2 plus h is more than 2. I need to substitute here. So it is x plus 2. Wherever x comes, let us put 2 plus h plus 2. Putting h 0, I just get 2 plus 2 and my answer is 4. As we compare, the function value is 4, the left limit is 4 and the right limit is also 4. So in this problem, the left limit, the right limit and the function value all are equal. So we can declare the function is continuous at 2 and hence it is continuous for all x belonging to R and there is no point of discontinuity. Subdivision 3, f of x is x cube minus 3 when x is less than or equal to 2. And x square plus 1 when x is greater than 2. Again, the problematic is 2. So we need to check the left limit, the right limit, the function value at x is equal to 2. Function value. Equality comes here. So let us substitute here. X cube minus 3. I will write 2 cube minus 3. 2 cube is 2 into 2 into 2, that is 8 minus 3, which is 5. Now I need to find the left limit. Wherever x comes, we need to put left. So 2 minus h. 2 minus h is below 2, it is obviously here. Wherever x comes, let us put 2 minus h. It is 2 minus h the whole cube minus 3. Putting h as 0, we get 2 cube minus 3 or it is 8 minus 3 and my answer is 5. The right limit, put x is equal to 2 plus h tending to 0. Here we are. Wherever x comes, put 2 plus h. So 2 plus h the whole square plus 1. As I put h tending to 0, I get 2 square plus 1. That is 4 plus 1 which gives rise to 5. I can check the function value, the left limit, the right limit all are equal. So we can say f of x is continuous at x is equal to 2. And we know being polynomial functions, they are continuous at all other points. Only thing to check is at x is equal to 2. As we conclude, f of x is continuous at x is equal to 2. We can declare f of x is continuous at all x belonging to R. Fourth subdivision, as we check the points of discontinuity for the function f of x equals sin x between 0 and pi by 4, cos x between pi by 4 and pi by 2. Notice it is less than, so pi by 2 open interval, whereas 0 equal symbol is there, it is a closed interval. When you are writing the answer, you must declare the interval properly. Now, we need to check this point where there is a split. Up to pi by 4, it is sin x. After pi by 4, it is cos x. So, check the point pi by 4. F of pi by 4, the function value. Here you have the equal symbol, substitute here. It is sin pi by 4. We know sin pi by 4 is 1 by root 2. In all the previous problems, we saw there is no need to put 3 plus h, 3 minus h like that. I can directly substitute also, because there is no denominator to cancel any such terms. Let us substitute. When we are in pi by 4 minus, that is left limit. For left limit, I am below pi by 4, so naturally substitute here. It is sin pi by 4 and my answer is 1 by root 2. For right limit, I am in pi by 4 plus, that is I have to substitute here. It is cos pi by 4 and my answer is 1 by root 2. So this I call function value, and this we call left limit, and the next one we call right limit, and obviously all the three are equal. So we can declare the function is continuous at pi by 4 and hence it is continuous for all x in the given interval. What is the interval? Closed at 0, open at pi by 2. So closed interval you put square bracket. For open interval, remember to put round bracket. Question number 4. At the given point x0, discover whether the given function is continuous or discontinuous, citing the reasons for your answer. x0, we need to check the value is 1. As we see the function, it is not equal to 1 defined in one way. Equal to 1, it is defined in some other way. So when x is equal to 1, we have 2. This I call function value. When x is equal to 1, it is 2. So the function value is 2. Proceeding to left limit, we need to check at 1. So let us put x is equal to 1 minus h and h tending to 0. As the given function can be factorized, x square minus 1 we write as x plus 1 into x minus 1. The denominator x minus 1 I can cancel whenever I apply limit value. Now the question is left limit, that is 1 minus. So just substitute. Wherever x comes, 1 minus h. As h tends to 0, 1 plus 1 is 2. So the left limit value is 2. The right limit, wherever x comes, we need to substitute 1 plus h, h tending to 0. As we substitute, it is 1 plus h plus 1. Again h becomes 0, I get 1 plus 1, that is 2. As we check all the three, the function value is 2, the left limit is 2 and the right limit is 2. All are equal tells us the function is continuous at x0 equal to 1. Without using h, I can directly substitute like this also. So you are comfortable in direct substitution or using h is up to your decision. Choose any of the methods. Second subdivision, x0 equal to 3. We need to check at x0 equal to 3 for the function f of x is x square minus 9 by x minus 3. if x is not equal to 3, and 5 if x is equal to 3. Obviously at 3 and above or below 3 it is different. So we need to check at 3 as quoted in the question. When x is equal to 3, the function value is 5. As I can simplify this, x square minus 9 is x plus 3 into x minus 3. A square minus b square pattern, which is a plus b into a minus b. I can cancel x minus 3, giving us only x plus 3. For the left limit, instead of using h, I just directly substitute. Put x is 3, I get 3 plus 3, 6. Right limit, I put again 3. It is 3 plus 3, that is 6. Now that we see, the left and right limit are equal, but function value is not equal. So this we say, f of x is not continuous at x is equal to 3.